Just a bit about myself. As mentioned, my name is Sabina Piras. I worked in California for about 6 years. Well, I'm American, as you can tell from my accent. I worked for a company called TY Land International for about 6 years as a bridge designer, where I worked on a number of new bridge replacement, retrofits, rehabilitations, and a lot of iconic structures, such as the one I'm going to be presenting on today. I moved to New Zealand, where I work for WSP Opus now about 2 years ago, and I'm actually going to be shifting south to the University of Canterbury in August to start my PhD on accelerated bridge construction. So the Idaho Avenue Pedestrian Overcrossing replacement, which is a mouthful, it's really a project that I was involved in from the preliminary design and structural assessment all the way through construction, and I was the primary bridge designer for it. So it's definitely one of the highlights of my career as a bridge engineer. How does this? Oh, you just press this?
Yeah, or the keyboard.
Oh, I can just click. There we go. All right, so the project is located in Los Angeles County, in Santa Monica, just north of the Santa Monica Pier. So I'm not sure if a lot of you have been out to California or Los Angeles, but this is definitely a very popular place amongst beachgoers. As you can see from the, So the bridge is located right along a bluff. If you've been out to California, you'll notice that the beaches aren't necessarily flat. A lot of the coastline actually consists of very tall vertical bluffs, which are very susceptible for erosion. The California Incline Pedestrian Bridge, it connects a series of shops, restaurants, and parks that in the Palisades Park area, and pedestrians take the Idaho Pedestrian Trail and they cross over the California Incline Roadway, where it connects to another pedestrian bridge. And then it crosses over the Pacific Coast Highway, and then they can access the beach, as you can see here. So you can see just how steep the Idaho Trail that pedestrians have to go down is about 10% grade. About 15,000 cars travel on the California Incline Roadway every day. And then, as you know, PCH, Pacific Coast Highway, is a very popular, or is a very crowded road. So it was important to the city of Santa Monica that we looked at this bridge. And so as you can see from this photo, the California Incline is actually in construction. This bridge replacement is actually part of a $20 million project that was funded by the city of Santa Monica. During the replacement of the California Incline Road, it was actually a project that I was also involved in. And the city of Santa Monica saw this as an opportunity that while they have this bridge, this road shut down for about 17 months, hey, let's take a look and see, hey, let's look at this pedestrian bridge. It's not getting very good assessments during inspections. So we're definitely on a time crunch because construction had already started on the roading below. So the city of Santa Monica commissioned TY Land International to first do a structural assessment of the existing bridge. This is the bridge shortly after it was built in the 1950s. So we started off with a structural assessment. As you can imagine, California is earthquake county. So it did have issues with seismic detailing. I do recall the pier columns were the stirrups were spaced at 300 mil spacing, really minimal reinforcement. So it was, obviously structurally deficient for seismic loading, but it needed a facelift. It was ugly. Just looking at it now. But the big thing, though, about this structure is because it was tied into the Idaho Trail, looking back, you can see this Idaho Trail wasn't paved. It was just a dirt trail, and although it doesn't rain a lot in California, every time it did rain, it was just cluttering the drainage pipe, as you can see in this photo. So the drainage pipe was completely clogged, So the water was building up at the top of this bridge. So the top of this bridge is supported by a pile, but all of it had eroded, so the pile was exposed. So someone came along and probably some asset management guy and put this H pile leaning up against the support. So I don't know about you, but I don't want to be on that structure during a high seismic event if it's just being supported by a pile, or a steel column. So that was a really big concern to us. So TY Lynn, we gave the city of Santa Monica kind of 3 options. We said, just get rid of it, and ask pedestrians to, kind of go around and then walk down. So that was kind of our preferred option for them. That was, going to be the cheapest. The second option was to do a seismic retrofit. But when we were looking at the kind of the footprint that we had, it was going to become really expensive. We looked at, using FRP around the pier column, but it wasn't very economical. So replacing it was the better solution. So the city of Santa Monica did fully fund this project. I think the bridge itself, the construction costs ended up coming around maybe 1.2 million, if I remember off the top of my head. So, and as part of this work, not only did we replace the bridge, but we made improvements to the trail leading onto it. So paving it, adding lighting, and obviously improving the drainage situation. These bluffs are highly erodible, so it was important that, and environmentally sensitive, so it was important that we could maintain as much of that as possible. So because the city of Santa Monica wanted this new iconic structure being built, we worked with an in-house architect, and some of the motives behind the architectural design of this was obviously we wanted an iconic landmark, something with visibility. As you're standing on the bridge, you have, full panoramic views of the Santa Monica Pier and the Pacific Ocean. And obviously, we needed to be quick. Construction had already started. The road was shut down underneath. We needed to get this design started and completed and built within a really small time frame. So we looked at a few alternative alignments. We were really restricted with our footprint. Just looking back, we have this, there isn't much room to put a column on the east side of the roadway. We're literally backed up against the bluffs. And then to the west side, the road kind of it's another set of cliffs. And so our footprint was really small. Our soil wasn't very helpful. So, and then we also had to be within the city right-of-way line, which is what RW stands for, not retaining wall. And then because this is a pedestrian bridge, we wanted to meet ADA requirements. So in order to be ADA compliant, this bridge had to be like a mile long. It was way too long. The existing trail up ahead that led into it was about 10% grade. Obviously, we couldn't regrade that trail and make it longer, so only part of the bridge would have been ADA compliant. This was another alternative we looked into. Eventually, we did get an exemption to not be ADA compliant because the existing bridge had a staircase. The trail leading into it was an ADA requirement itself, so we were able to work within a smaller footprint, which helped our budget and was less obstructive. And again, reiterating, this is a very highly environmentally sensitive area, and we still had to meet that minimum vertical clearance over the traffic below. So we finally got approval. Okay, we don't have to be ADA compliant. We can have staircases, which was very critical in order to be within that small amount of space. So our architect came up with some options, and we actually presented them to the public, and the public ended up selecting the final design, which is what you see on the screen here. So the final design was 48 meters in length. It was cast in place, cast in situ concrete, so no pre-stressing. The foundations were concrete board piles. The design started November 2015, finished in February. Construction began in March and was completed by July. The full structure opened up to the public on September 1st of 2016, So you can see how quick we had to act. This looks like a small bridge. It looks like, oh yeah, a few months of design doesn't sound like an issue, but with all the planning involved, and just, I'll get into the design a little bit more. It really was a time crunch, and it was a team of one. So it was a lot of work, but it was well worth it. Any architects in here or aspiring architects? All right, cool, I won't offend anyone. So the architectural design was, it was inspired by the ocean. So looking down on it, it has a spiral curve, which was influenced by the nautical shell. The V column was inspired by the vertebrae of the whale, as our architect called it. So those were kind of the two features from the architect. Now, this is the final rendering. Now, in the actual design of the bridge, we have two columns over by the cliffs, and they're actually well exposed. Our architect didn't believe in gravity and absolutely hated those columns. He fought us he refused to actually put renderings of those two columns up against the cliff, but we kept telling him, no, you need to put those columns in. The bridge can't span that long, it's too thin. But they eventually got built, but that was just kind of one of the funny things that happened during the detailed design, is he just would not render the columns, and then he kept hiding them behind the cliffs. So that's what working with an architect was like. Again, the final design, we have the slope ties into the bridge, and then we have a staircase just along the western end as you're looking over the ocean. And we had stainless steel railings on both sides. And the city of Santa Monica wanted to keep their sign, so we replaced the sign, the city of Santa Monica sign that lit up at night, and then we provided LED lights along the whole bridge. So it was really beautifully done. And here's some more renderings. So, as I mentioned, working with the architect was fun. We did a lot. We played around. He did all the modeling in Rhino, and we played around a lot with how wide, how narrow can we make, the V columns, the V pier, at what angle can we optimize it without really influencing the design too much. So it was a really interactive. I sat next to him during the entire design process. It was really interactive, and we were able to take his Rhino model and import it into Civil 3D, and import that also into our design software. So it was really cool how much we used technology during the design of this. So the codes we used were AASHTO, Caltrans seismic design criteria, which basically, it's basically our seismic design criteria, and then the California Building Code, just because it was for pedestrians and had a staircase. The design programs we used were Larza 4D. Larza 4D is a lot like SAP. The only difference between Larza and SAP is that Larza has that fourth element, which is time, which is really good for cable-stayed structures, but SAP was really good program for this. And then, as I mentioned, our architect used Rhino that we used to import. So as you can tell, as engineers looking at just this model, we don't have an abutment. We actually modeled the abutment as a roller supported by a vertical spring, because we didn't really rely on the soil at the top of the slope. We knew it was just a matter of time, or in a large enough event, that soil would just erode, had the possibility of eroding. So we wanted to make sure that the bridge can hold itself up without needing an abutment. But as we know, the west side, or to the left, it's a really stiff structure, and on the right side, it's a very flimsy structure. So we got massive displacements, seismic displacements, up to 10 inches, which is a lot. It was a lot. It was a lot to design for. A structure like this, you don't want to have to design for inelastic demands, but we did. Unfortunately, it was just the nature of it. It was high seismic area, high seismic loads. Looking at just the cross-section, it's a super narrow cross-section, so doing seismic detailing, especially at the column joints, proved to be quite challenging. I mean, we really had to sharpen our pencils during design. As you can see, again, the columns are missing. But the main structural component of our superstructure is we really utilize the barrier, that vertical barrier element. It's pretty tall. I was actually worried that people wouldn't be able to see over it, so our architect put me in there, I'm 5'2", to show that yes, you can see over the barrier. But we really did rely on that barrier for the majority of our flexural and torsional capacity. One of the challenges that we found during this detailing, we modeled every single concrete fiber of this section. We modeled every single piece of rebar because we needed all the capacity that we could get. The span was really high. The torsion demands were really high. But because we had to provide railings on both sides, having a post pocket actually kept us from being able, we wanted to get the rebar as high as possible and get as much, negative capacity as we could. And so we ended up going with drilling connections rather than post pocket, just so that we can get the rebar as high as possible. We did a section, we used a program similar to Response called Extract. I'm not sure if any of you have heard of it. It was developed in California, but it's a section modeler where we can discretize the section, to thousands of, pieces, and really get the capacity of our section and really design it for torsion, because it was the utilization was pretty much at 100%. This is our Civil 3D model that we basically imported our Rhino model into Civil 3D, and we put all the reinforcement in. There isn't a single straight line on this structure. So it was really important that we could get all the reinforcement modeled in there appropriately. Especially at the joints. We took section cuts so that we could put something on paper, but we knew that you physically couldn't build this bridge on paper. So we, being the unique structure that it is, we actually just gave the contractor our 3D models, which is starting to become more popular. But on your typical highway structures, cast in situ, 1 or 2 lane or 1 or 2 spans, you can get away with just having paper plans. But for this one, there was no way of actually defining the curvature. Everything was so asymmetrical in every direction. The widths and the heights of the superstructure constantly changed. There was no set, formulas to define it. So we did provide the contractor with a 3D model, and they did have to get a sub-consultant to create the false work for the V pier, and I know they used a carbon fiber. So again, this is kind of a cross-section of all the reinforcement sections that we provided. So again, you can constantly, it's like getting an MRI. Every section is different. So some photos. This is the demolition of the existing bridge. Pretty janky. And then this was a photo taken during construction, heavily reinforced. During construction, the formwork actually did catch on fire, which was not ideal. And then this is the final product. So since its opening in 2017 or 2016, it's won a number of awards. So it's definitely something that T1 Land International is very proud of. You can see in the back the Santa Monica Pier. So it really is an iconic structure for the city of Santa Monica and something to really be proud of. And another sign, those are the 2 columns that aren't in any of the renderings. So, and just some more photos. But yeah, you can see in this bottom photo just how limited we were on room to put our footing. We really had to optimize. And because there was an existing structure there, we had to place our piles strategically around the existing piles and keep them a certain distance away so that we can get as much utilization out of the soil as possible. But even though, because we were building on a bluff, we could only utilize half the soil spring stiffness anyways. So anything moving towards the ocean, towards west, we weren't going to get much capacity. So it proved to be a very quite a challenging design seismically. And that's my presentation. Hope you guys enjoy.
Thank you. It's really interesting.
Yep.
So let's have some questions.
So obviously you're pushing it pretty hard.
Yeah.
Do you have much issues with your peer reviewer? So your independent review team?
Yeah, so we had an independent review team, and we didn't have any issues with it. They, they were getting pretty much the same, demands as we were. It was really during the design that we were we tried everything to get the piles to work. We were getting really large, because of the flexibility, really large tension in our piles. Yeah, it was tough. I mean, we were looking at just every way that we could model it, model the stiffness, model cracking, using vertical soil springs. Yeah, we eventually obviously got it to work. Here it is. And we were even trying to justify, okay, maybe we don't push it the full, over strength. Maybe we only push it to the demand, but the demands were so high. And we just looked at different pile configurations. We looked at maybe maybe we support it a certain way. Do we change the concrete properties? But to answer your question, sorry, no, we didn't have too many issues with our peer reviewer.
But they need to go to the same level that you did, because obviously it's
They didn't go to the same level that we did, but they did see, our models. They did run their own. It was a little bit more simplified as ours was, but no, I don't recall having too many issues with the peer reviewer, but they did make comments that they were pretty valid points, so, yep. Mm-hmm.
What measures did you consider possible further erosion or drainage runoff from the pathway above the bridge?
So we trusted our drainage team to provide a solution. So actually erosion on this bridge I worked on the design of the bridge underneath. Even though it looks like it's a roadway underneath, we designed it as a bridge because the piles had to act as essentially columns in the event of erosion. And we were estimating, the geotech was estimating up to 5 to 6 meters of erosion during a seismic event. It was really bad. And we actually worked with the geotech and put soil nail walls up along the bluff to try to keep it as stable as possible. So we designed for up to 5 meters of bluff failure. So when we worked on this design, we actually had very intricate surveying done of the bluffs. We knew every single crevice. We knew exactly, how long our piles needed to be because, the bluffs moved in, So we had a full scan done for the survey. So.
And during that survey, obviously you would have picked up the remaining as-built piles from the previous bridge, and were you, I imagine you were relying on those to help stabilize the slope?
Not really, no. If anything, it hinders us because now you have that group reduction factor, right?
Makes sense.
So.
Excuse me, would you please go back to the slide with the model, please?
With the what?
With the model.
But yeah.
I'm talking about computer model. Yes, this one here.
Mm-hmm.
Obviously, by looking at the bridge itself, which means potentially you use a line element.
What was that? A line element?
Yeah.
Yep.
The beam element rather than some sort of plate element to model the.
Yep. So SAP 2000 and Larza, they both have parametric section definitions. So I modeled the entire section along its CG. Now the center of gravity changes for each individual section. So I defined every single one of those frames as a different section name, as a different section property, because it's constantly changing in width and height. So with SAP 2000 and Larza, what you can do is you can say, your frame starts as this section and then ends at this section, and you can have it change throughout that. So The only thing that I needed to do then was make sure that I modeled the CG correctly, but then the section itself changed along there. And then what I could do is I can go to that frame element and find out what the stresses were along it. Does that make sense? Did I answer your question?
Yes, but I'm starting to think about if you use a plate element, potentially you can understand the torsion, particularly for the different deck. Because if you just use the line element, which means potentially how going to make a judgment for the torsion.
Well, you're still going to get the torsional stiffness from your section, right? So you can still get your demands. So I'm not using this program to determine capacities at all. I was only using it for demands. All the capacities I did by hand. So, or on extract, which was the section definition. But with torsion, I ended up doing it by hand, which is harder. Torsion needs to be taught a little bit more in depth in schools. It can be difficult. Note taken, especially on awkward object, non-symmetrical shapes. So.
You mentioned that you had a ductile mechanism. What was that? Was it ductile? Where is it on?
Oh, it was hinging. It was hinging actually on the V pier, of all places. Yeah, which is not where, we wanted it to hinge. So.
Bottom, both top and bottom?
No, just at the top, and then also the piles because they were getting into tension. So. Yeah. Those two columns to the right, those were just super flexible. Obviously those weren't hinging, but yeah, everything was just getting, basically that V pier, that staircase was just supporting the whole bridge, and the rest of it was just flopping around. So we were getting about 10 inches of displacement demands with those two columns, which was just it was really loading the rest of the structure. And then because of the curvature, things wanted to twist really funny. We weren't getting, you want it when you're looking at, a pushover design, you just want it, okay, I'm gonna look at it longitudinally, I'm gonna look at it transversely. I had to look at it in every such direction just because of the way that the bridge wanted to move in a seismic event, so.
Did you have any issues with like pedestrian dynamics or anything like that?
We don't, in the US, we don't model pedestrians for seismic loading. Oh, vibration, no, not for this one, no. So, we did look at that, but no. It's concrete. Concrete usually doesn't have issues with pedestrian
It's a rocky
vibration.
shape, isn't it? It's probably going to twist as much as
Yeah, it's gonna twist. Yeah. So usually it's steel and wood, steel and timber that have issues with pedestrian vibrations. Yeah.
Did you find any particular issue with the temperature?
Nah, it's California. It's one temperature all the time. Yep.
In a project with this level of complexity, there's always going to be some uncertainty. What were those uncertainties that remain to exist even by the end of the project?
Geotechnical.
Do
Yeah,
you see-
geotechnical.
Nothing else?
Yeah.
It was
Structural, you're always trying to predict the behavior, right? So you get your dynamic models, when you run a dynamic model, you're looking at, 30% longitudinal, 100% transverse, but really how does the bridge really respond? And we did look at, vertical accelerations here, and so the behavior in a seismic event, you're trying to predict it as best as possible. You're trying to shake it in every such direction, and then you're doing pushovers, and you're just, God, please don't push over in this direction, it's going to be a lot more flexible, but it's really just how the soil is going to respond. I guess at the end of the day, so long as the soil doesn't erode, if the pile fails, it's still in the ground, right? I'm just kidding, don't ever design like that. But it's really just how that soil is going to keep up, because we were really just relying on every bit that we could, so.
For the modeling of the piles, did the stiffness of the springs horizontally influence the whole thing?
Oh yeah, absolutely, yeah.
Because that's probably the most challenging thing to model, because you're not very sure how it's going to behave in
Yeah.
terms of the K value.
Yeah,
How you
exactly.
gauge the purity of the building and the bridge.
Yeah.
Did you design for a range?
What was that?
For your spring values, did you have quite a big range?
Yeah, and obviously, if you're in one direction, you're only gonna have, partial, actually, the Geotech told us, because we were working on such a narrow footprint, he said if the bridge moves west, just ignore soil springs. He's like, they're just useless. Like, you're not gonna get any soil resistance, but obviously if we're moving towards the cliffs, we're getting all the soil stiffness in the world. So it was really the movement away from the cliffs towards the ocean that was controlling our design.
I think it helps to understand the direction of the movement, because fundamentally, according to using code, they indicate if you not actually if you use equivalent static method or use response spectrums, because fundamentally if you use equivalent static method, and which means potentially which direction will be the main direction point, because potentially we just only have x and y direction which if you put it into a plane, which means each direction is perpendicular to each other. But for the shape of the building like that, it's pretty hard to identify which the major movement direction. So
Yep.
it's very, very tricky, and how you got to, sometimes you can, in text or in set, you can rotate the angle, try to see how it deform, and finally, once you see the vibration shape, you can identify, okay, I can estimate this angle might be the main direction, and then you adjust the
Yep,
angle.
so that's what I did.
With this.
Yep, so I ran a response spectrum on this for the dynamic analysis, and I did look at, almost like an orbit, what's gonna give me the worst case. Unfortunately, earthquakes don't read the code. So it's gonna do what it wants. So yeah, that's what I ended up doing, is just finding that worst direction, that you're gonna get the worst loading, so.
Is the American code for seismic loading, does it combine
Mhm, it's the
percentage of
same.
one? Yeah.
Yep, it's the same, yeah, 30 and 100.
Yeah.
Yep.
So, of course, okay, thanks.
Good.
So you just
One last question.
Yeah.
At what point did you have any contractor involved in the design?
Did I have a contractor involved?
Yeah.
Nah.
Design, or was it after the design was completed?
So at T1 International, we actually had contractors within our company, as they worked along with us. Just, they obviously had their own projects, but they always provided a lot of support. So we always consider them as part of our design team, just kind of our construction team. So we did get a lot of input from them. Obviously, the construction, this wasn't like an alliance type of project, but because there was a team, construction had already started underneath prior to the design of us even starting, we were able to work with that team a little bit more, and it helped us not only really for constructability, but it was more just cost, because we were so limited. It's a $1.2 million bridge, and we're looking at, it's the architectural features that cost a lot, the coloring of the concrete. The formwork was the most expensive thing on this project for this V pier. We're even contemplating, do we even put formwork on? We have stainless steel railings and LED lighting. So it's all those things that we had to take into consideration to determine our final design, so.
Was it self-compacting or concrete?
That's a good question.
It was a lot of steel. That's what I meant.
That's a good question.
If you do self-compacting, you do it.
Yeah,
Yeah.
that's a good question. No, but we had a construction joint, actually.
Foam would look like a sheet, so you could actually.
Where's the,
very interesting.
we did have a construction joint right above the deck level. So obviously you had to do that in 2 pours. I honestly don't know if it was, that's a great question. I don't know, I'm sorry.
Is the concrete naturally that coloured, or is that painted?
It was colored concrete.
So it was you expect it to be white rather than painting?
Yeah, yeah. So it was lighter gray. So it had a nicer finish to it. It was a little bit more expensive, but yeah, I think it turned out quite beautifully, so.
Yeah, the white paint just peels after time.
Yeah, it does. Like the existing bridge looked a little janky, so, but because this is Los Angeles County, it does get tagged. I had friends that went out and visited, and they were showing me photos of it, like getting tagged, and they have to go out and paint it and maintain it, so it's just the nature of what happens.